Hello everyone. I just wanted to drop a little video to explain a little bit more on the rotating sky to you using our rotating sky explorer that we'll be using for lab next week. I also wanted to go through a little bit of this rotating sky homework and give you some pointers there in case you needed some. As it comes time to turn it in, I'm going to let you turn that in by Friday. And then also just talk a little bit about celestial coordinates since we're working on those as well. So here we go. First off, the Rotating Sky Explorer, you're going to download this, and there's a short 1-minute video that shows you how to download this onto your computer. Go ahead and open that, and these labs are really going to be handy for us this semester. I'm going to open this one to do a little demonstration called the Rotating Sky Explorer. You're going to use this one. And what this does is it shows the Earth here and our location on the Earth, and you can actually click and move this around, and as you do, notice that on the Earth here it's moving also. And then when you move your location, you'll notice that things change a little bit on this screen as well. That's your local view, your horizon view. So for Geneva, our latitude is 42 degrees north and about 88 degrees west for the longitude. Okay, so we set that up as such. And what it looks like from here is that our local sky at this latitude and longitude looks like this. Now you can show labels on this to see all that's there, and you can click and drag on these things here. Note that the celestial sphere view, this is kind of the Earth and space view. It has the celestial equator labeled. It also has the North Celestial Pole and South Celestial Pole. And then over here, it gives the North Celestial Pole and the Celestial Equator at our particular latitude and what it would look like. And there's us in the little bubble there. And so let's see here. That's in my way. Let's get that out of my way. And so let's add some star patterns here. The Big Dipper, Orion, and the Southern Cross are good examples. One in the north, one in the middle, and one in the south. And what happens is when you actually start this animation, the Earth begins its rotation, and as the Earth rotates, the celestial sphere remains stable. But as the Earth rotates, it actually causes things to rise and set in our sky. And look at, there's Orion swinging up to the top of the sky and now setting down here in the western horizon. Remember, at 42 degrees north latitude, we know that the angle of the North Celestial Pole above our horizon is 42 degrees. And the celestial equator then is going to be at an angle that's perpendicular to that, or 48 degrees. And if I click on that, it'll show that celestial equator there, 48 degrees. It's of note that all stars rise and set then at an angle of 48 degrees here in Geneva. And that's 42. That's our 90 minus our latitude. All right, and so you can kind of see the stars swinging around. In fact, I can make star trails on them, so you can kind of see their paths as they rise in the east there at angle of 48 degrees. Get up to the top point in the sky, which is the meridian. Remember, AM and PM. Here's our meridian. Orion's on a meridian. Before the meridian is antemeridian or AM, and past the meridian, post-meridian, PM. And that's the highest point, and then it starts to set. Orion starts to set here, and again, it's along our celestial equator. So this is pretty nifty. Another thing is to remember what circumpolar was. Circumpolar is stars that never rise or never set. The Big Dipper here swings down low by the horizon but never sets. In fact, I click on this little circumpolar region, and you can see that the Big Dipper lies within that. Likewise, there's a lower part, because we're on the side of the Earth here, we are on the northern hemisphere. There are some parts of the southern sky that we can't see, this blue region down here. When you look at it in our local sky here, it's this blue region, the never rise stars. And you can see here that the Southern Cross here swings all the way up close. As from our view, though, we can't ever see it because it never comes above. So we'll never see that particular constellation from our latitude. All right, so I just wanted to show you how our concepts apply when put in motion. Now, this is a handy little simulator, and you're going to use this. I'm going to have you identify the height or the altitude of some of these Big Dipper stars, I'll have you pause the animation. You can actually slow it down so you can control the movement of the Big Dipper a little bit more. I'll have you stop it here on the meridian for upcoming assignment next week. And when you click on the star, it shows you its altitude. And so you can kind of see the altitude above the horizon as it hits the meridian. And so that's the Big Dipper there. And you can kind of see that. And I'll have you go to different latitudes and longitudes and see how high that Big Dipper is. All right, so that's the Rotating Sky Explorer and the NAP labs that you'll be using. Let's go to the worksheet here on the rotating sky. There's a few questions that you're using your textbook for. The motion is stars rise and set. The Earth's rotation causes that. I'm just going to ask you to sketch in a little celestial sphere, just a big sphere with the Earth in the center. That's all I'm really looking for there. A cluster of stars has an angular size of 2.5 degrees. I wanted you to know that there's in 1 degree, and I'll go ahead and draw this in here. Oh. Let's try to get my thing working here. So 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds. Now, this is just kind of how it works. Like if you're standing here looking at a star cluster, and the star cluster here in the sky is 2.5 degrees arc wide. And my stylus is not drawing very well here. 2.5 degrees wide. Then in order to get how many minutes, you would take 2.5 times 60. Oops, and I saw that I drew that in wrong. Minutes only has one of those little dashes there. So in order to get the number of minutes of arc, it's would be, 2.5 degrees times 60 minutes to get that. That's going to give you your answer in minutes. And then the one to give you in seconds is going to be, your 2 point, whatever you get in minutes, you're going to take that times 60, or your 2.5 times 60 times 60. An index finger held at arm length. One index finger at arm's length is about a degree of arc or so. 2.5 would be like, oh no, that's not right. It's about 2 degrees of arc wide. I'm sorry, I can't remember off the top of my head. I think it's 2 degrees. So it'd be like 1 1/4 index fingers for this answer here, 1 1/4 index finger. Down here to number 6, altitude and azimuth, remember, is the altitude is how high something in the sky, and the azimuth is how its direction, the direction you have to look. Remember, north was 0 degrees azimuth, east is 90 degrees azimuth, south 180 degree azimuth, and west 270 degree azimuth. So if something's halfway between the zenith and the horizon, that altitude's got to be about 45 degrees, because remember, straight above you is 90 degrees and the horizon is 0 degrees. And if something is in the southwest, okay, that would be a little bit between 180 and 270, right? That's 180 is south and 270 is west. So right between those, that would be like 225 degrees. 225 degrees azimuth, okay? So you don't actually have to look at the book to see these. You can actually get them. The altitude of a rising star is 0 degrees, and the azimuth of a star in the southeast would be 135 degrees. So doing a little bit of extra help for you there. Some information about circumpolar, you should be able to do that. And then down for this part, just to help you out a little bit with this part, what you're going to do is draw a little oval and then draw a dome over the top of the oval. And you're going to draw yourself in there, or a person in there. And remember, north is usually always on this side. And remember that the North Celestial Pole is going to be equal to the latitude, the degree of the North Celestial Pole. So the latitude here is 45 degrees, so the North Celestial Pole is going to be 45 degrees. And of course, the celestial equator then goes from the eastern horizon to the western horizon, and it's perpendicular then to the North Celestial Pole. So in this case, it would be right here like this. So this would be your celestial equator, and this would be your horizon down here. Okay, and then of course your zenith point is up here. And so that's what you're going to basically be drawing. This part down here is kind of recognizing where stars would go on your little diagram. So a star, 270 degrees azimuth, that's going to be facing the west, and southeast is 135 degrees. So you just have to recognize that these are directions. Then when you come here, west is, again, 270, and north is 0 degrees, right? And then something that's halfway up in the sky, its altitude would be about 45 degrees, because all the way up is 90 degrees. So 2/3 of 90 degrees would be 60 degrees. And of course, 30 degrees would be 1/3 the way up in the sky. 15 degrees would be 1/6 the way up in the sky. Okay, and so that's what that's all about. Lastly, plotting these stars on your little diagram, A through E. For example, the first star, 200, is at 270 degrees, so we're going to come all the way over to this location. I'm going to use a different color here so we can make it a little more clear. So in the west here is where we're looking for star A, and it's halfway up in the sky. So we come to the west and we come up halfway in the sky, we would put our star right about there. That's where star A would go. Okay, on our diagram. If you imagine that it's kind of on, if an imaginary bowl is over the top of our little horizon diagram, that star would be on our side of the kind of dome of the bowl that's there. And you do that for the rest of the stars. So that's kind of how you do that stuff on this homework. All right. The last thing I want to do is just to introduce to you celestial coordinates. Whereas before we were talking about the horizon system, and that was where things are located in a local horizon given by our altitude and azimuth. The equatorial system is going to be attached to the stars themselves, right? So we'll talk about why use the equatorial system and a little bit about it. But first, just some basics. Remember that latitude and longitude on the Earth is how we find location on the Earth, right? It's a set of two coordinates. It's based on the equator here, which is at 0 degrees. That's the center of the Earth, and latitude is your angle above the equator, either 30 degrees above the equator or 60 degrees above the equator, that kind of thing. And longitude is your angle east or west of the prime meridian. And so if you go this way, you would be going east longitude, and going this way, you'd be going west longitude. And together, the two coordinates give you locations on Earth. This location would be one example. And this location, see that there's a latitude line here and a longitude line, and it gives you location. Very similarly, there's a coordinate system for the stars, and it's called the equatorial system. It's because it's based off the equator. But if you imagine the Earth in the center of our little celestial sphere here, we have the celestial equator here, and then we have lines of celestial latitude, and those would be called declination lines. So the celestial analog for latitude would be declination. So your degrees above the celestial equator would be plus declination. Your degrees below the celestial equator would be minus declination. And that's how they recognize the position of a star above or below the celestial equator. And then you have this sort of celestial prime meridian. It's called the 0-hour line of right ascension. And right ascension is what they call the celestial longitude. So from the 0 hour of celestial longitude, you just start going around the circle here, and that's the position of a star around the Earth that direction. And so these two coordinates, declination and right ascension, can give us the location of a star. And they give it a location regardless of where you're at observing from Earth. So the advantage of this system is that these star coordinates are the same for someone in Australia as they are for here in the United States. If I am viewing something in my sky in the United States, and I call up my friend in Australia and say, hey, you should see this, object in my sky. It's 45 degrees altitude and 0 degrees azimuth. And, my friend in Australia be like, that's great, mate, but my sky is completely different. Um, so if I gave my friend in Australia the um, right ascension and the declination of that star, then that my friend could then identify when that star is in their sky and therefore then see what I'm seeing. So scientists all over the world like to use this coordinate system because it's simpler and does not require earthly coordinates and latitude and time of day in order to recognize where a star is in the sky. And so here's a greater look at that diagram. Declination above or below the celestial equator. If you're going above the celestial equator, it's plus declination. They don't use north, they use plus. And if you go under the celestial equator, it's south. It's not south, they don't use south, it's minus declination. And the right ascension is given in hours. Notice the 0h there. Oh, here's my declination slide. Excuse me. You can see plus degrees going above the celestial equator and minus degrees going below. The max declination you can get above the celestial equator at the north celestial pole is plus 90 degrees and minus 90 degrees at the south celestial pole. Right ascension, as I said, is measured in 0 to 24 hours instead of 0 to 360 degrees. Every hour is 15 degrees of right ascension. And the reason they did this is we're going to get to next week, but it's about your star viewing time. We'll revisit our friend in Australia about that. But the 0 point hour of right ascension here is where the sun, when the sun is in springtime at the vernal equinox, this is when we have the 0 hour, or this is where we mark the 0 hour, like where the sun lines up at when the vernal equinox takes place. So they call this a vernal equinox point. And so that's 0 hour of right ascension. You go to 2 hours, 4 hours, 6 hours, go around the circle, right? And that is the celestial longitude coordinate. So it's real easy to find the positions of stars using these coordinates. You'll use this information to answer the questions on the celestial coordinates worksheet. And that one you're working on as well right now. I have a video to help explain celestial coordinates, so hopefully that'll help along with this video. And then, you have this assignment here. I often get questions about a couple of these, so I'm going to go through one here for you. It says, jump into number 5. Suppose an observer in the northern hemisphere determines that the diurnal motion of a star keeps it above the horizon for 16 hours. What this means is that the star rises for 8 hours, gets to the meridian, and then sets for 8 hours. Okay, so, and because it's more than 12 hours, it's because it's in the northern hemisphere, you're in the northern hemisphere, it's likely that that star is in the northern celestial hemisphere also. Because we're seeing it for more time. It's closer to us on the celestial sphere. So that's why it's 16 hours versus 12 hours would be kind of like right along the celestial equator. And if we're viewing a star from the northern hemisphere and we only see it in the sky for like 8 hours, then it's definitely probably in the southern celestial hemisphere. So the answer for this question would be northern celestial hemisphere. And then how much time elapses between this star rising and it crossing the meridian? That would be 8 hours. It would rise in the northeast and set in the northwest. Okay, and then down here, an observer working the summer solstice, notice that the sun circles about the sky at a constant altitude of 23.5 degrees. And then the observations are interrupted by the angry bear. What color is the bear? Well, the place you would be on Earth where the sun circles around you all day and night at the summer solstice would be on the North Pole. Believe it or not, the sun stays up all day and night circling around in that location. If I was to demonstrate that, I can actually demonstrate that on my rotating sky explorer here. If we go ahead and type in 90 degrees north latitude to take us to the North Pole, Now notice the red region, which is our circumpolar region. All stars are circumpolar at the North Pole. You see that? And this will be on your quiz as well. What are the stars doing on the North Pole? They're all circumpolar. They circle around all day and night. When the sun's out, of course, it's the one that's circumpolar. All right, so kind of trippy, right? All right, so hopefully that helped you with the 2 homeworks for this week and understanding things moving in motion a little bit. I put out a little video to show how to download these NAEP labs and this Sky Explorer business. So you can take a look at that with that assignment. And I hope this helped. Please email me with questions, and thank you very much.